Hey everyone, we're going to go ahead and do notes for 1.1. This is in your journal book. It's on page 4. So we're going to go ahead and I'm going to kind of walk you through some of the vocab and some of the problems here, and you should be able to follow along. All right, so first we're going to start with some of the vocab. So the first one is a parent function. And what I need you to know about a parent function is that mostly it's just like your basic function or your basic equation or graph, if you want to think of it like that. And the key thing here is that it doesn't have any shifts. And so what I mean by that is it's not like moved up or down, or it's just like your most basic version of your function. The next one is a transformation. So a transformation changes the parent function by either, it could shift it, so I'm thinking like it could shift it up and down, left or right. It can change its size, so they can make it kind of wider or skinnier depending on the function. It could also go ahead and reflect. So a transformation does, each transformation does one of those things. So you might have a transformation that causes your function to move down, and then another one that moves it left, and then another one that makes it, skinnier if you're talking about like a quadratic or something, and then another one that would reflect it over the x-axis. So could be multiple transformations in one function. So now we're going to talk about the different kinds of transformations. So all of these right here are different types of transformations. So the first one is a translation. You probably remember this from geometry, but basically what this means is it slides your function. So think of it on your graph, right? So it slides your function, the shape stays the same, it stays the same size. Normally what we call this is it slides your function either left or right. So basically it's just moving it around on your graph, over to, or, left to, right to, kind of thing. Could move it up to or down to or whatever. A reflection is a flip. So it flips your graph. A lot of times it flips it over an axis, so like over your x-axis or your y-axis, but generally what we say is it flips the graph over a line of reflection. So I just want you to remember that the line of reflection a lot of times is one of your axes, so like your x-axis or your y-axis. Not always, but in a lot of times it is. All right, so the last two are vertical stretch and vertical shrink. And so what I kind of want you to think about this is if you have like a parent function, for example, think about like your linear function. So think about something like y equals, well, actually, let's talk about quadratics. I think that'll be easier. A lot of you guys have some experience with quadratics. So like y equals x squared versus y equals, let's say, 2x squared. So what does that 2 do to my function? And this is where that vertical stretch or vertical shrink will come into play. So if you think of it as like slope, right? The 2, if you think of it as 2 over 1, what you're essentially doing to all of your x values after you square them is your like rise over run is 2 over 1. It means you're stretching it more, the rise part as opposed to the run part. So if you think about a quadratic, like a U-shaped graph, and you apply a factor or a multiple of 2 in front, you're essentially stretching it more vertically than you are horizontally. We call that a vertical stretch. And so a lot of times what we'll call this is like your A value or your factor. That's the number out in front. So the absolute value of that value, we'll call it the A value, is greater than 1. So that's how you can tell in an equation that you're going to have a vertical stretch. It's because this number out in front, like here I knew there was going to be a vertical stretch because there was a 2 out in front of my x squared. This would be my parent function. This would be my function with a transformation. And that transformation would be called a vertical stretch. A vertical shrink is the exact opposite. So it's your absolute value of your A value so basically what we're going to say is that your absolute value of your A value is less than 1 but greater than 0. So no negatives, but it has to be less than 1. So going back to our example with x, if this were our parent function, then something with a vertical shrink might be 1/2 x squared. So again, think of this as like your slope, you're rising 1, but you're running 2. So think about what that would do to your graph. You're stretching 1, but you're stretching it like out 2. It's going to make that U-shaped graph kind of, wider basically. And so it's going to cause a transformation to your function. All right, so what we have here are just kind of like your basic parent functions. So notice we have the family right here, which that basically just means the type of function by its name. So we have a constant function, we have a linear function, absolute value, and quadratic. And those should be ones you're already familiar with. So a constant function, the rule or the equation would just be like y equals or f of x equals 1. And so this is what the graph would look like. So we call this the parent function for a constant function. Linear is y equals or f of x equals x. Absolute value has those absolute value symbols, and quadratic, of course, is x squared. Now, if you look at the graphs, a constant number is just like a straight horizontal line. So if it's f of x equals 1, it's a horizontal line through 1. A linear function, y equals x, just means that it's going to be, there's no y-intercept. The slope is 1, so it's just a linear equation passing through the origin. Absolute value, what makes that one special, and I want you to kind of remember some of the key words here, is that this is a V-shaped graph, and then a quadratic has that U-shaped graph. So you might want to write down, V-shaped and then U-shaped for our notes under those two. Okay, so down here we talk about domain and range. So remember, domain means all possible values that would work in this equation. So in other words, domain refers to x's, range refers to y's. So like in this one, we're talking about like what x's work in this problem. And so the number of x's that work here are all of them because it's a constant. And the range, since what y's work in this problem? Well, there's only one y value for every point that's on that line, and that's 1. So the range here would only be 1. Another way of writing this is something we call set notation, and that's something we're going to be doing in honors quite frequently. And that's where we use that little curly bracket. And if I wanted to represent range, I would use y's because that's obviously for range. I would say y, and then this means all values of y, such that y is an element of the real number system. So that just means all real numbers. So this is a fancier way or more mathematical way of saying all real numbers. And then what we say here is, since we only want it to be 1, we say y equals 1. And then we close the bracket. So this is kind of what range is in kind of like a shortcut way. This is the more mathy way of writing it, and we're going to get in a lot more writing it like this as well. But that's something we're going to be doing a lot of. If I was writing range and domain and range for linears, it's going to be all real numbers. There are no gaps, all x's work, all y's work. So all real numbers. For absolute value, because there's a minimum, and same thing with a quadratic, there's either a min or a max. The x are all going to be all real numbers, but the y values, so for your parent function, the lowest y value is 0, and then obviously it goes on forever. So that's why it's y is greater than or equal to 0. Same thing with the quadratic parent function, the lowest y value is 0, and therefore your range would be all real numbers greater than or equal to 0. To write this in set notation for this range, I'd kind of start off with my symbols here. All values of y such that y is an element of the real number system. So that just kind of basically means all real numbers. I'm going to say y is greater than or equal to 0. And then obviously, since this is the exact same, we could use that same one for this one. To write all real numbers, so I'm going to write the domain for this one. This time I'm going to use x's because I'm talking about domain, which means x values. So this means all values of x such that x is an element of the real system. And since we're stopping there, basically there's no restrictions, we're just going to end our curly bracket. And this is another way of saying all real numbers. So I know in our comp books we're going to be asking you to kind of dictate or kind of write out what it means to be in set notation. And so we'll talk a lot more about this, but this is kind of what I'm asking you to kind of outline. Like, what does all this mean? All right. So then we get into some practice. And so it says, identify the function of family where it belongs, compare the graph to the graph of its parent function. So we're going to kind of quickly do this one. I just want you to kind of think back to that other page where it asked you to identify the family. So it's the answers are either going to be constant, linear, absolute value, or quadratic. And so what I want you to do is kind of get in the habit of noticing the type of graphs for each type of function. Like you should recognize that this is linear. This one's a constant. This one's absolute value because it has that V-shaped. And then finally, this one's a quadratic. So it's going to be important that you recognize the function by the look of the graph. And so those are your 4 basic ones that we're going to be talking about right now. The other part of this asked you to compare the graph to its parent function. So what I want you to look at is the equation. So if your parent function is normally like a linear equation would be like this, right? That was from the previous page. What happens here is all of these numbers, if you look at your equation, all of these numbers cause my function to do something different. And so what this means is that each of these numbers plays an important role. So first of all, this negative out in front causes my graph to have a reflection. The 1/4 out in front, that's going to be your, remember we talked about that A value, that's going to be your vertical stretch or your vertical shrink. So in this one, because it's less than 1, the absolute value of that number is less than 1, we're going to call this a vertical shrink. And then the +8, this is kind of like the number that's being added or subtracted to the whole function. That causes a translation. So what that's going to do is cause my function to be shifted up 8. So think about like the y-intercept, right? So normally at a parent function, the y-intercept is at 0, 0. Now the y-intercept is at 8. So that we would say this is up 8, and that's a translation. So for this one, a constant function, normally our parent function for a constant function is already at 1, remember? That was kind of our family, our parent function. So now if we're down here at -3, that's actually a shift of down 4. And so you can call that a translation, or you can simply say that it moved down 4. There's no other transformations on this one. If you look at the equation, in a constant function, there are no variables, like no x's, I should say. And so there's not going to be like a vertical shrink or a vertical stretch or anything like that. For your absolute value, there's a 5 out here. And so remember, what does that number out front do to our graph? If our normal absolute value is just f of x equals absolute value of x, this 5 is that a value. So because it's greater than 1, that a value, we're going to call that a vertical stretch. So that's that a value out in front causes my function to kind of be shifted or like stretched more vertically than it is horizontally. Okay, so for quadratic, on this one, you can see that there's something happened to so your parent function is y equals x squared, right? So you can see that there's a -1 here, and then there's a +4. So this -1, what that does to my function, that's going to be your left and right. You're shifting left and right. If it's a -1, this is going to seem a little backwards, but if it's a -1, it's going to shift to the right 1. If this would have said x plus 1, it would have shifted to the left 1. Again, that seems a little backwards. And then this number on the end that's being added to the whole function, that's called our k value. We'll talk about that in a little bit. That number is another translation, and that it's going to be moved up 4. So kind of like that linear function over here, we talked about that number on the end causing our function to be shifted up 8. In the quadratic function, same kind of deal. It's a number +4 at the end of your equation causes your function to be shifted up 4. If this were a -4, it'd be shifted down 4. So kind of the same deal. All right, so on this one, it asks us to graph the function and its parent function, and then describe the transformation. So what we're just looking at is like what happens. So what I want us to kind of get in the familiarity with is I want you to think about what the parent function is like. So if this is linear, so y equals mx plus b, this would be your parent function. This is your constant function. I should be using f of x here, so I will. Remember that constant function has a y equals -1. And then this is your absolute value. So these are all your parent functions. And again, all I did is just kind of pulled them from this page here where we talked about our 4 different types of parent functions. So that's the constant, the absolute value that we're going to talk about in the linear. So then it asks us basically what kind of transformation. So we can do this in 2 ways. We can graph it and kind of look and see what happens. And so you can graph it by hand or you can graph it using your calculator. I'm going to go ahead and graph it on our calculator. I'll show you how this works. So I'm going to go ahead and type in my y equals. So all I did here is go to y, and you can kind of see my screen here. I'm going to go and type x, and that should be a linear function. That's your parent function. And if I put in the next function, which is linear function x minus 7, go back to your y equals. Let's go down to y2. I'm going to type in x minus 7. Notice that the graph is shifted down 7. So kind of see that one with the glare. So basically all I did here is take this function and shifted it down 7. So you can verify this graphing calculator to kind of see that what the graph is doing, but also you can look at the equation. This number on the end, okay, that's your y-intercept, causes my function to be shifted down 7. So ultimately what I want you to get in the habit of looking at is the actual equation and not having to graph them every single time to determine what happens to my function. This is that constant function. It was normally your equation is at, not negative 1, be positive 1. Normally positive 1. If I shift it, if I'm now at negative 9, that's a shift of down 10. So it went from positive 1 down to negative 9 is a shift of down 10. And then your absolute value, so again, remember that's that V-shaped graph. We can look at it. What do you think this plus 1 is going to do to my graph? So again, it's kind of like your y-intercept over here. It's being added or subtracted to your whole function. And so what happens here is this plus 1 causes my function to move up 1. So again, you can verify that, and I'll show you that one on the graphing calculator. For those of you who don't, I'm just going to clear those out of here. If you don't know how to put an absolute value, you hit your math button, and and you go over to num or number, and the absolute value is the first option. So absolute value of x should look like, if I graph it, should look like a V. And then if I go back to y equals, I'm going to go back to math and number, absolute value of x. I'm going to get out of those absolute value symbols, and I'm going to put plus 1 at the end. So what this should do is move my graph up 1. So notice how the graph is literally the same thing, just shifted up 1 spot. So again, obviously you can check it with your graphing calculator, but I'd like us to get in the habit of kind of looking at the function itself and looking at the equation to be able to determine whether or not it is shifting up, down, left, or right. All right, so this next one is a quadratic. How did I know? Well, because there's an x squared. So my function would be h of x equals x squared. The only thing that's different is this negative. So when we look at that number being multiplied by x, or in this case x squared, when there's a negative out in front, what that does is causes a reflection. And so what you will notice, if I go back to my graphing calculator, I'll clear these out. Whoops. And if I go x squared, and then I type in negative, make sure you use the negative sign and not the minus sign, you should see your original parent function. It's kind of showing up there. And then you can see your reflected function. The glare here, can you see it there? And so you can see that it really, all it does is it reflects it over that x-axis. And again, you should be able to know that from looking at the equation. So that's kind of where I want us to get at. This is another quadratic, and again, I knew that because of the x squared. So this is my parent function, would be just x squared. So how is this one different? There's that 1/8 out in front. This is going to be that a value. I talked about that before. When it's 1/8, that's going to be when it's less than 1. If you think back to your notes, right? We think back to this page where we said that's going to be your vertical shrink. When your a value is less than 1, or the absolute value of your a value is less than 1, but greater than 0. So this is going to be a vertical shrink. And so what this one does, I'm going to go back here. So I'm going to type in 1/8 x squared. So what this do is make my graph look a little different. So notice that, see how much wider it gets? Can you see that? See how much wider that graph gets? It's like, I know the glare is kind of hard to see, but this wideness of this graph, that's because it's stretching it more this way than it is this way. So it's stretching it horizontally. Call that a vertical shrink. All right, last one is an absolute value. Again, what gave it away? Well, the absolute value signs. So this one is, my parent function would look like a V, and it's just going to be absolute value of x. Again, there's a number out in front. So what this is going to do is going to cause either a vertical stretch or a vertical shrink. Because that number is greater than 1, this is going to be a vertical stretch. And so that's what happens to my function as we change the a values or change the different types of functions on our graph, although the numbers, it causes my function to do something different. So feel free to graph these and kind of get in the habit of kind of looking at what the parent function does compared to what the new function does. Eventually what we're going to look at is something like number 11. So number 11 gets into, it says identify the family of functions, identify what the family of function is. In other words, is it constant, linear, absolute value, or quadratic? And then describe the domain and range. It also asks you to use your graphing calculator to verify your answer. So on this one, again, first let's start with like the family. You should be able to look at this function and see what family it belongs to. If you see those absolute value symbols, it belongs to absolute. So that's the family of functions it belongs to. It says describe the domain and range. So I always think it's helpful to look at the graph of the equation to be able to describe the domain and range. So I'm going to go ahead and clear out my other stuff in here. And I'm going to type in this equation. So I'm going to start with 1/3. And then I'm going to go back to math and numbers so I can get that absolute value symbol. And I'm going to type in negative x. Again, use the negative sign, not the minus sign. I'm going to arrow over, and I'm going to put +4. So that's what my equation looks like on that one. Okay, I think maybe that helps a little. So that's what my equation looks like if I'm going to type it into my graph. So this negative inside here is going to cause some issues. And so let's take a look at what happens. So because the negative's inside the absolute value, it's not going to be a reflection. So it's a V-shaped graph. And it asks us to kind of talk about domain and range. So you can think about the transformations of this function, like what does the 1/3 do to it? It should have made it wider, right? And it has that vertical shrink, basically. It's stretching it more horizontally. What did the +4 do to my equation? Well, it moved it up 4. But for this one, they're asking about domain and range in particular. So for all absolute value equations, and I can't stress this enough, all absolute value equations, the domain will always be all real numbers. So what that means, when you write domain, I'm going to have you write it in set notation. So we're going to call this set notation. And so we say domain, or I just put D. We use the little squiggly brackets. And if I want to say all real numbers, I say x, and put like a straight line, which means all values of x, such that x is an element of the real number system. So what this literally translates, so math language, it means all real numbers. And then I end it with a little curly bracket. Range is the only one that's going to be different than all real numbers. So for absolute value, because of absolute value is that V-shaped graph, there's going to be a min or a max. So this one has a minimum looks like at +4, right? That's the lowest y value. So what essentially I'm asking you is what y values work in this equation. And the y values that work in this equation are basically anything from 4 on up. So I'm going to go back to my equation, and this time I'm going to use y's, because again, I'm talking about range. So I always start off my set notation the same way. So for domains, I use x's, for range, I use y's, but I start off by saying all real numbers. So y such that all y's are element of the real number system. But now I define exactly what y's I'm looking for. So I want y's that are greater than or equal to +4. And then I end my parentheses, or my curly brackets. So what this means is all real numbers where y is greater than or equal to 4. So this, you have to kind of say this in the beginning part anytime you say set notation, because basically it says we're talking about real numbers. And then if there's something specific that you're defining, then you say, oh, I want all real numbers, but only the ones that are greater than or equal to 4. And what that allows you to do is to kind of get a more specific answer rather than just saying all possible numbers. All right, last but not least, we have a kind of a story problem here to end. It says, gave you a table that says time and distance, and it asks you first to say what type of function is this. So you probably remember this from Algebra 1, way back in the day. If you look back, you can kind of see, oh, look, my x's are increasing by 1 each time. You also might notice that your y values have a pattern too. If you notice, they're increasing by 12 every time. When that happens, that's called a constant rate of change. So again, thinking back to Algebra 1, what you're doing here is you're noticing that there's a constant rate of change. This is a linear function. And it's linear because there's, as x increases by 1, so you'd say as x increases by 1, y is increasing by 12. So as x increases by 1, as long as y is increasing or decreasing by the same amount each time, like adding or subtracting by the same amount, then it's linear. I like this last question. It says, if the biker's teammate, so if this is like talking about a biker's here, they ride at the same pace. So again, think about what that means. The same pace refers to like their rate, or in this case, their slope, because we're talking about linear, but they leave 1 hour later. What type of transformation does this represent? Well, if they leave 1 hour later, let's think about what that would do to my graph. So if you're 1 hour into the trip, and let's say you're the second person, you're the teammate. If your friend is always one hour into the trip, that means you're starting at 0 here. So when they're at 12 miles, you're still at 0 because you haven't left yet. When they have ridden for 2 hours, since you're going the same pace, you've only ridden for 12 miles. And so forth and so on. If they've ridden for 3 hours and 36 miles, that means you've only ridden 24 miles. So what happens here is you notice that your rate or your slope stays the same. You're still increasing by 12. But what this does is it causes a translation. And so what this is going to do is, it's kind of like if you think about a graph, right? You're starting here, but it's almost like if this is your friend's data, you're kind of starting down here, increasing. So when they're at 0, 0 at the start of their race, you're like 12 miles behind. And after 1 hour, they're at 12, right? After 1 hour, you would be at, 0, 0. And so what they're getting at here is that this is going to be a vertical translation. So in other words, that's when we talked about like shifting up and down. So it's a vertical translation. In other words, it means that you're shifting this function down 12. So if you're leaving 1 hour later, because the rate is still the same, the only thing that's doing is you're literally keeping something with the same slope. You're just changing your starting value, which causes my function to be shifted down 12. All right, so this is a long video for the first one, and I would write down any questions you might have over this, and then when I see you in class, we can kind of go over anything that you found to be confusing. Feel free to rewatch the video, especially the stuff on like using the calculator or set notation, and that way if you have questions, you can ask when you see me in class. All right, thanks guys.